Well, good morning, everyone. I'm going to get us started now. Welcome, all of you, to Inotherm. This is the Inotherm Colloquium from the Department of Mechanical Engineering at MIT. I am John Lienhard, a professor of mechanical engineering at MIT. I work on heat transfer and thermodynamics and other topics. And at points in my career, I've also worked quite a bit on high heat flux engineering. So I'm really very interested in today's topic, which is cooling of the first wall of a fusion reactor. This is the solid surface that separates the plasma from whatever working fluid you're using to carry the heat away. And as you can imagine, the heat loads on these reactors are quite intense. All the more so because today's reactors have become much more compact. Today, we're fortunate to have Professor Dennis Whyte from MIT as our speaker. Dennis is the director of the MIT Plasma Science and Fusion Center, and he is also a professor of nuclear science and engineering at MIT. He's received a number of awards in the fusion area: Fusion Power Associates Leadership Award, Nuclear Fusion Journal Prize. He is also a fellow of the American Physical Society, and his work is in magnetic fusion energy, plasma surface interactions, and accelerators and surface analyses. And in particular, he's been very involved with the SPARC project at MIT, which has led to the smaller generation of fusion reactors. Today's agenda is as shown here. We'll have a presentation for 50 minutes or an hour or so, and then we'll have Q&A. The process for submitting your questions is to put them, use the Q&A button on the toolbar and put your question in there. The questions are being moderated in the background. They'll be sent to me, and then I will read them off, and Dennis can respond to them at that point. We're also interested in suggestions for future topics and speakers going forward in Inotherm. This webinar is being recorded, and it will be posted on YouTube in a week or so. So if you missed a step in here on the talk, you can go back and look at it again. If you really loved it, you can recommend it to friends and relatives. So without further ado, then I will stop sharing, and I will pass the floor over to Dennis. Dennis?
Thanks, John. I'll just share my screen here. Does that look okay? Good. Well, thanks for the invitation, John. Excited to talk about this topic, which is near and dear to my heart. I really want to thank all my colleagues at both MIT and Commonwealth Fusion Systems and internationally as well too, but particularly I want to thank the students from my 2263 Fusion Engineering Design class, which many of the materials and in literally the last third of the talk is taken from their presentations. And thanks to all those students and those who've participated in this. So the focus here, this is an enormous topic. So I'm just going to bring up front that I'm going to focus only on magnetic confinement fusion because presently it's the most likely first fusion power plant. I'm going to focus on a particular configuration called a tokamak, which is a toroidal magnetic configuration, because it's the most advanced concept. And I'm going to even further focus down to high magnetic field tokamaks, as John mentioned. This is the MIT Commonwealth Fusion Systems approach, which leads to very compact and high power density devices. And the outline is as following. First third, I'm going to talk really about fusion and tokamak and the constraints from the heat exhaust viewpoint, sort of lay the stage for the challenges that are here. Then show about what a high field tokamak, particularly arc and spark, plus the heat exhaust challenge that comes with those particular designs. And then finally, I'm going to conclude with a case study in heat exhaust innovations, which is basically turning our idea towards, for instance, a green fuel of using fusion to make hydrogen. So why are we interested in fusion energy? You've probably heard of this before. It's like, well, it's pretty exciting. Fusion energies, it's literally the energy source of the universe because it's what powers the interior of stars. You get no polluting or carbon emissions on Earth, which is a big deal. The fuel is freely available and inexhaustible. You can generate it anywhere and at any time. Meltdowns are physically impossible, and you can actually eliminate most long-lived nuclear, almost all long-lived nuclear waste actually from the design. You don't have proliferation because in the end, it can basically supply energy theoretically to all of civilization forever. So it sounds like a good deal, right? It's scientifically feasible, but it has not yet been harnessed. And I think as we go through this colloquium, you'll actually see that, one of the things that was in front of us was actually getting this to work. But one of the clear challenges about actually making it to be a practical energy source is going to be heat exhaust. So what does it take to make fusion? So fusion fuel is free, which makes it very nice, but it requires very special conditions to be an energy source. And namely, it has to be in the plasma state. And what does it require? So it's kind of like making a fire, is that in the end, we put together wood, we spark it with a particular temperature, and then we put it into configuration so that it stays hot, and basically that one log burns another. So that's a simple way of thinking about it. But we do this it's in a different state called the plasma state. And it's a very unique set of conditions. That namely, the density of the fuel is very, very small. It's 100,000 times less dense than air. Yet the plasma temperature is higher than the center of the sun. So it's at 100 million degrees. You put those together, it's actually order of an atmosphere of pressure. So this is one of the reasons why fusion is so inherently safe. The fuel is actually at very low pressure. And then in the end, it has to basically contain the energy for about a second. If you meet these three conditions together simultaneously, it will start to make net fusion energy. But I'm not, this is going to be a lesson about fusion physics. It's just like, why do we care about this from the heat exhaust point of view? The fact that the plasma density is 100,000 times less dense than air means the system requires vacuum. The fusion fuel must be in a hard vacuum. And then over there, this thing about energy confinement means that it requires magnetic field, or B, insulation, which is there to actually hold this thing together because it's 100 million degrees and has to contain its energy for that. So what are the basics of fusion? So over here on the right, we have the cartoon that we usually think of in this, is that it's at its heart that fusion fuses light elements like hydrogen in the center of the sun. We use particular ones, deuterium and tritium, which are the heavy isotopes of hydrogen, into heavier elements. You get a total mass deficit, which is E over C squared. So what you get is that an energy is released because of this rearrangement of the nuclei. It's in the velocity squared, it's in the kinetic energy of the fusion products, which come out of this. So in this case, it's going to be a neutron and helium. I'll get back to the details of this. A key point in this is that if you look at the probability of that fusion reaction happening, the probability that particles scatter off each other just by elastic collisions is much greater than the fusion probability. So what this requires then is that fusion always requires confinement. And confinement, namely meaning you allow the scattering and the thermalization to occur, and then once in a while a fusion reaction occurs. So in a star, that's provided by gravity. On Earth, we actually have to do this through the Lorentz force, V cross B, or EV cross B, I guess I should have said. It's proportional to the velocity and the strength of the magnetic field. And this requires then that the fuel is in the plasma phase. When you put these together, it must be in the plasma. That's why I'm the director of the Plasma Science and Fusion Center, because we have to understand plasmas to make the fusion work. So what these mean is that this unique set of requirements also leads to a very multidisciplinary approach to heat removal. And I'm going to start with a cartoon before we get into any engineering details to say, like, why is this such a special consideration? Because this is the physics, basically, of fusion that sets this. So at its heart, a fusion energy device, and really I'm going to start almost immediately talking about like making energy on Earth from fusion, not just as an academic exercise. It basically heats itself and recycles neutrons internally from the tritium. So this is get a little bit more specific to the fuel cycle we use. We use the heavy forms of hydrogen, deuterium and tritium, which are shown here. We fuse them together, and what we actually get out at the other side is a helium, and we get a neutron. And now you see that why fusion is so attractive is that in an energy balance, you can see there's a factor of like 1,000 energy gain for the products that come out. But the energy of fusion is contained in the kinetic energy of these particles, and it's mostly in the neutron because it's it has the least mass in this as well too. So this is why we have plasma physics, because over here, this temperature is required of the average kinetic energy of the particles at 0.01 mega electron volts. In normal parlance is 100 million Kelvin. So this is why we need plasma physics to basically understand the confinement that we get to this. So now really the next part of this is like what happens to the energy. So 20% of the fusion energy is in ions. It's in a charged state. It's in the helium in particular. And that heats the plasma through collisions. This is how plasma in the end heats itself in order to sustain the fusion reaction going on. This is what happens in the center of stars. This is also why it's so safe, because it relies not on a chain reaction, but actually heat keeping coming back into the plasma. So this is still the plasma physics discipline. But now to the heat exhaust point of view, very, very important is that even the most energetic particle in ions, or the photons that can be produced by the plasma collisions, have all less than 1 micron range in materials. So anything that has to do with the fact that the plasma is going to come and lose this, what I call plasma heat, is going to go only through a surface at some boundary interface, which I'll get back to. So it's a pure surface heat removal issue. The neutron contains 80% of the energy. It escapes magnetic field confinement because it has no charge. And then it interacts with an engineered blanket surrounding the fusion plasma. So this is what extracts the heat. So in the end, here's the cartoon. It comes out. We basically slow it down from 14 MeV. We slow it down by about a factor of 1 billion down to room temperature. And this happens through neutron atom collisions, which have a mean free path on the order of about 10 centimeters. That leads to volumetric heat, and then that leads to electricity. So I point out here, now we're starting to deal with nuclear and thermal engineering, because this is the majority of the heat that's actually released by the fusion system. The blanket then must contain lithium, because it has to capture the room temperature neutron, and that produces the fusion fuel and actually some extra energy for internal recycling. So in the end, we basically capture this neutron on a lithium-6 at room temperature. It produces a triton. This triton is actually just simply recycled back into this. So in the end, this is why I said the fuel is inexhaustible and free. It's because it comes from deuterium and lithium, are the actual external fuels. And now we're bringing in other disciplines like nuclear and thermal engineering and radiochemistry to basically deal with this rather special environment. So in the end, we have a recipe, that's the physics cartoon of what we're doing about making fusion power. And the recipe for fusion energy engineering success is well understood. You basically have to make 3 things happen. You need to make net energy gain, which is kind of self-evident from a net energy system. And here, this is capital Q, we define it, which is our little cartoon that we have over here on the right, is that there's some medium, this plasma state making fusion. The fusion power is coming out into engineered objects around the side of it. We have some input power into this to start getting it hot. So it's basically our match in the fire. So to make a net energy system, this fusion power must greatly exceed the input power, because otherwise you don't have net energy from it. Typically for a practical power plant, this is on the order of 10 to 20, something like that. But that's not enough, because you also must meet economic targets. This cannot have an arbitrarily low power density, because you're going to spend a fair penny building all these complex objects around it. So what we have in the end also too is we think about fusion power per unit size. So in this one, I'm going to particularly use this as although there are many ways to break it down, the simplest way to think about this, because it's a containment system like the sun, we talk about the surface area of this plasma. And this heat is going to come out in some way or another out into that surface area S. And so we need to consider something about getting a certain amount of fusion power per unit size or power per surface area, because that's going to drive the economics. And then our little cartoon again, some cold fluid comes in and you get heat out the end on the top of it. So the final thing that you have to have for a practical energy system is you have to reach thermal steady state, because you have to be continually exhausting the heat that's coming from the fusion energy. So quickly talk about how do we do this? So the way that we do this is that we have to have confinement, and we do this with magnetic confinement. And in particular, the tokamak magnetic confinement configuration provides the best fusion performance and gain in the power density, because without this, you don't have to worry about heat exhaust because you're not making any fusion power. And it's really as simple. It's basically a toroidal set of nested magnetic fields, which are in a twisted helical shape for reasons I won't explain. But basically, what this really in the end exploits, and this is what this picture on the left shows, is that it exploits the fact that it's a closed toroidal topology and it's axisymmetric. This is a very proven insulator to the 100 million degree plasma. So I thought I'd have a little fun with it. Fusion physicists never talk about the magnetic field really as an insulator, but for thermal engineering colloquium, I thought I'd sort of cast it like this. So what's happening from the physics point of view is that this plasma state, which contains the charged particles, the magnetic field is forcing the particles to execute tight orbits around this due to the Lorentz force. The reason that it's closed the long way around is because there's no Lorentz force parallel to the magnetic field. So you have to force the magnetic fields to move back around themselves. This magnetic field, from an insulation point of view, is a very strange beast, you have to say. So it's highly anisotropic. So if we build this configuration, this is basically the shape of the plasma. Across those tubes, which is across the magnetic field, it's an excellent thermal insulator. So it has like a thermal heat, it has a thermal conductivity of like a milliwatt per meter Kelvin. I'll just point out that also that this kappa is like proportional roughly to 1/b squared. So that, in other words, the higher the strength of the magnetic field, the better an insulator is. I'll get back to why that's important. So this is interesting. We have a grad T in this, which is on the order of a few hundred million Kelvin over a meter. Like, it's the most spectacular thermal insulator in the universe, actually, in the end, when we do this. And actually, if this is a little backwards because you don't usually think about it this way. What this really is setting, though, is that it tells you already, this tells you about a power loss flux, which is sort of on the order of a megawatt per square meter before we've done even an inch. Along the magnetic field lines, where there's no Lorentz force, it's an even stranger medium because the particles have very, very high kinetic energy compared, like a million times higher than what we're talking about at room temperature. So when they can just freely stream, they have extraordinary properties. Like the heat conductivity can be 10 million watts per meter Kelvin, which is just like, you can hardly imagine what kind of heat exhaust capable it is. And it's interesting, it's proportional to only to the temperature of the plasma. So this can actually lead to heat fluxes in the direction along the magnetic field lines of gigawatts per square meter. It's actually been measured in the laboratory, even at MIT as well too. So what this means is that material objects are impossible actually at the location of fusion, because what this really acts like is a thermostat. And the places where the plasma touches surfaces basically fall to a certain temperature to satisfy this crazy heat conductivity that the plasma has. So in the end, the fusion happens by definition away from any material object. So actually, in the end, what we build is this thing that looks like on the right. You have to have this toroidal configuration. In the end, what we design is a set of closed, particularly in the big blue ones here. What we end up producing is a set of electromagnets to produce this magnetic field, which are going to be on the orders of 10 Tesla, as we'll show you later on. And we conduct these, we put these in a circle, in a toroid. And so what's very important here is the plasma is inside the electromagnets. So this defines the cage, if you want to think of that, for the fusion. And we'll get back to the engineering of why this is important. So in the end, what we actually build are electromagnets and some things that are going to be inside it to take the heat that's coming out from fusion. So let's get to brass tacks. Fusion heat exhaust is hard. One, geometry. And it comes from the physics of fusion. So on the left, I've got like a cartoon level, but it's appropriate. If you think about fission, which is sort of our cousin, right, is that you've got the red things are fuel rods. Fission is occurring inside of them. And that's volumetrically heating those fuel rods. You basically put water, usually pressurized water, at the bottom of this. It pushes water past those surfaces. And then what you do is you've got a whole bunch of design tools about optimizing the volumetric to the surface area, to the things, to the pushing of the water past it. And people that actually have appointments in mechanical engineering at MIT have thought their entire career about optimizing this problem because it's really important, because obviously setting the power density and the heat effectiveness is really important, because and the reason this happens is fission happens at room temperature. Look over on the right. This is horrible from a heat removal point of view. It's because all of the heat is generated in a single volume that literally cannot touch anything. So every single joule of energy that's produced by this 100 million plasma, however you're going to get it out, has to come out through a single surface. And that single surface is going to be surrounding the plasma. So this already geometry disfavors you, because you're going to bite almost, and in fact, in some sense, it's because of the requirement of confinement of the plasma itself. So let's put in some numbers on this. And it's really because I've set this up, again, not as a physics talk, but really to try to understand the constraints of this. And it's really because of the unique form of the energy that fusion has. It imposes special constraints. So again, it's a cartoon. So here we have our cartoon over on the left. We've got a magnet that's around here. Somewhere in the center is a plasma that's creating all this fusion heat. And then we're going to talk about the two forms of energy that come up. So I'm going to talk first about the neutrons, because they're a very special kind of power. And what I'm going to set this at is a power of the neutrons per surface area of around 4 megawatts per square meter. I'm not going to show the details of this, but almost every economic analysis of fusion shows you have to reach a fusion power density that's kind of on this. And that's why I'm going to use this as the example. So the neutrons basically stream out essentially isotropically out into some large thing. So what is it? So the neutrons move through that surface area S into this bulk. And the physics of neutrons, because they have no charge, set the E-folding distance of this heating at approximately like 0.2 meters. It's not exactly, but it's close enough. So what this immediately tells you is that you get a localized heating of around 20 megawatts per cubic meter, somewhere out in this medium that's stopping the neutrons through collisions. And this is the key economic parameter, is actually the volumetric heating caused by the neutrons, which are 80% of fusion energy. And why is that? Well, it's because in the end, this is your economic product, and you're going to build all this other stuff to contain this, but in the end, it's that power density which is going to tell you about whether or not it's going to be viable. Another key points to this is that the neutrons are losing their energy, and so they slow down by about a factor of a billion, by literally knocking into sort of that's blanket atoms, through collisions, in fact, literally with the nuclei of the atoms, not with the other. So all the atoms are displaced about once per week in a fusion device. So this is kind of hard to imagine from a material science point of view. This means this will require a replacement. The other part is that from the nuclear physics point of view, all of these neutrons are allowed to produce helium in bulk through transmutation. And materials react very poorly to insoluble helium in them. And in the end, this also requires an order of a meter of this distance to thermalize the neutrons, shield the magnets, and it must contain lithium. All these are constraints which come from the fusion physics. Then you talk about the surface, the plasma heat. Well, that's interesting. That's only 20% of the heat in the system, but it's already at 1 megawatt per square meter in our little example. So plasma heat has to be moved at that surface. So what is the challenges here? Is that because this little red line that I've shown here is the surface of where this is coming out, must be high fidelity vacuum interface, because what's in the white area of that must be at high vacuum, and the other parts are not because they're engineered, at atmospheric or a higher pressure. What is this? Surface heating with plasma ion species is also difficult, because if it comes out from the plasma, then you get atomic removal of the materials because they have enough kinetic energy to actually knock out the atoms from the surface. And it's also highly variable heat flux, that you can get heat fluxes greater than 10 megawatts per square meter. And it has to do with the nature of the heat conduction that I showed you before. It's so incredibly sensitive to the temperature of even the cold parts of the plasma that it varies by about 2 or 3 orders of magnitude around this. The other part is parallel to the magnetic field heat flux can be greater than a gigawatt per square meter. So what this forces you to do is take parallel magnetic fields, which eventually must touch something in this object, and they have to be highly aligned surfaces to allow grazing angles, typically order of 1 degree. So this means any distortion of this surface makes it very hard from an engineering point. I'm not going to talk about that in detail, but it gives you a hint of the difficulty of the thermal engineering of those surfaces. And then it also has to be compatible with this rather weird set of fuels, which is hydrogenic fuels and helium. And with establishing very high local temperature gradients, because even with the highest thermal gradient species that we have, you're talking about like hundreds of Kelvin per millimeter of thermal gradients in this upper surface. And you've got this corrosive and weirdly interacting hydrogen and helium species with it. So basically this eliminates most engineering materials almost immediately from consideration. We almost always look at as refractory metals and things like silicon carbide. Okay, so okay, man, that's that looks really daunting, that problem. And it's like, so should we actually care about this problem, or are we close enough to fusion to care about this? And the answer is yes. And the reason for this is, I'll just show you that I'm not going to go into the details of why this is, but remember the key thing that we need to obtain first of all is energy gain, fusion power out over E in. And this is the curves that it collapses to. It has to do with the things I showed about before of the fire that we're making from the fireplace we're making from fusion. And you can see in particularly tokamaks, the configuration I showed you on this plot, are pushing their example points right up to the point where we're almost at Q of 1. But you can see on here, there's a new, and in fact, that crazy thing that you might have like, have you ever actually achieved 100 million degree plasma? Yes, quite routinely, actually. You can see all the points kind of lined up over here. So the exciting thing is that there's a device called now on this, there's a new point on this to be placed on there experimentally called Spark, which would actually achieve net energy gain for the first time. And so I also realized there might be people in the audience that is like, that fusion, I've heard about fusion, but isn't it all kind of like, you know, really slow and it has kind of stalled? And yes, that is correct. It did stall. But it wasn't like that for a long time. Starting with the invention of the tokamak in about 1970, it actually beat Moore's law in terms of those requirements to get net energy gain. It was going up by orders of magnitude only in a few decades, and actually ended with experiments that actually showed that showed fusion power and those points on the plot that I showed you before. The problem that came out is turned out that the progress stalled because of technology, not because of science. And it stalled because you had to build, and this makes sense from a heat conduction point of view, is that I showed you that there was a magnetic field of proportionality to the heat conductivity. To make it hot enough and to make enough fusion power to keep it going, we had to build the world's largest experimental device called ITER in the south of France. This is taking like about 30 years to basically come to fruition. And mostly I would argue, other people would argue slightly different arguments, it's mostly because of how big it is. Okay. So the proven way to decrease fusion device scale and accelerate fusion energy development is to achieve high magnetic fields. Again, this is not a talk about fusion physics, but this is really important to look at this. Because if you look at the fundamental things about what we talked about, namely gain and fusion power density, gain scales proportionally to the magnetic field strength to the 5th power and something like the volume of the device. And the fusion power scales like the linear, R, by the way, is the linear size of the toroid. Okay, so the volume scaling like R cubed. And B to the 4th power. So you see these incredibly compelling nonlinear wins with increasing the magnetic field strength, but those are impossible. So the other way that you can achieve the requirements is to make R large. That's ITER, because basically it had a fixed amount of magnetic field it can make with superconducting technology. So our approach was we looked at this, and then it turned out we had a gift given to us, is that if you could just double the magnetic field, look at those, you're improving by factors of 16 and 32. Could we do something such that what we could do is decrease the volume, time, and cost of fusion using the exact same physics as ITER by greater than factors of 10? So the answer is yes. But the other important point, as I talked to John when we discussed this, was like, but it also brings the challenge, the fusion power density is going up. This is a good thing because it makes fusion more economically interesting, but it also increases the fusion, the thermal engineering challenge significantly. And that was what happened. And while we were waiting for ITER to be constructed, a breakthrough happened, which was Rebco superconducting technology emerged at industrial scale that essentially allowed us for sufficient performance to double the magnetic field in superconducting magnets. I'm not going to, there's whole other sets of talks about that. I'm not going to talk about that, about how to get there. But I'll talk about the implications of it. So in the end, is those simple formulas that I showed you have way more experimental and theoretical work behind it. But basically, in the end, you can collapse the energy gain that you're getting, capital Q, with these isocontours. Reactors sit up here in isocontour of a gain of around 20 or so, and it collapses down to linear size at capital R and the strength of the magnetic field that you can make. And as those equations showed you before, what happens is that if you're limited, like you can only get up to a certain magnetic field, like around 5.5 Tesla at the plasma, then you have to build a device that has 6.5 meter major radius. That's ITER, right? But if you can open up the right-hand side of this, is which that new superconductor does, you can push down on the same physics curves to the point where you get ARC, which is our prototype pilot plant that actually makes electricity. And the reason that you can't make this smaller is because the neutrons have to be stopped by the blanket. So in the end, you run out of space. And if you keep going down even further and you throw away the electricity emission, you can make a device even smaller with the same physics, and that's called spark. So this is to orient you to, and here they are at scale in this. And this is what doubling the magnetic field does. It basically takes you from a device that's of that size, and its mission is almost exactly met, in fact, by this device down here, 40 times smaller in volume. And that's what spark is. From an economic point of view, it's rather quite simple as well, too. This pushes ITER, which is a very valid science experiment, but its economic profile looks not extrapolable to the private sector. Instead, what happens is that also goes down by basically a factor of 40. And now we're talking about $1 per watt, which actually puts it in play with other energy sources. So thus, we built a plan between MIT and Commonwealth Fusion Systems of developing the new magnet. And that's actually going on right now, and we should be tested this summer. So make these new magnets, put them together in a device called Spark. With this, what we call the Kitty Hawk moment for fusion. It's 10 seconds at 130 megawatts, and that would be the first demonstration of net fusion power ever. So it's like literally the seeing, like that's why we say the Kitty Hawk moment. It's like seeing something fly for the first time. So it's very exciting. And that timeline is 2025. In fact, we just announced the site for where that's going to go. The physics design of this is done, and with the completion of the magnet design, we should be going further. And over on the right, which I'll get back to a lot more, is ARC, which is the 250 megawatt electric pilot plant that we have. So, and what we did was, because of the economic prospects, we actually launched a fusion company, a startup, Commonwealth Fusion Systems, that's partnered with the PSFC, and we're building this technology about pushing forward together with MIT doing a lot of the R&D, obviously, in education, and the company, focusing on commercialization. So this is very interesting, because Spark is a strategy to achieve fusion energy and power density ASAP, like 2025, but intentionally strategically removes the steady state heat exhaust emission. So it has a gain of 11, which check mark, has a power density of fusion power of 3 megawatts per square meter, which puts it in a check mark against those economic needs. But intentionally does not have thermal steady state in it. We picked this because you could actually have the plasma on for 10 seconds for the plasma. That's essentially in infinity, because everything equilibrates in the plasma. And we didn't use active cooling for the internal components because it provides resilience to our ability to actually explore for the first time this self-heated plasma. And it also has no blanket, because there's not sufficient space to shield the neutrons. So my perspectives on this, so you think about, oh, wow, 2025, we might actually see net fusion for the first time. I always think in my head, Spark is a big project, and wow, that's going to be an amazing thing. But I always imagine somebody like John turning around to me, in the control room of Spark. It's like, you did it, net fusion. When do you have a power plant? And here's my perspective on this. The science of fusion, which is not the perception, it's 95% or more demonstrated. And Spark will lay energy gain questions to rest circa 2025, knock on wood. But the challenge of fusion is I believe, turning towards economics, which has very special features and needs. And because its features that it's dominated by overnight costs, because you have no cost to the fuel. So you must decrease the volume and complexity to lower the dollars per watt. You have no marginal fuel and material costs. So therefore, availability is essentially everything that sets levelized costs. You have to have a strategic pathway to rapidly increase the availability, actually, in the first ones you design. And then 3, power density. You have to have high power density in this and I believe variable power output, which is a feature that fusion can actually do. Because what this will do is it'll identify and capture the beachhead markets for these kind of ARC class devices. And we have to develop energy capture technology that satisfies both 1 and 2 of these ones. And that's the heat exhaust challenge that's in front of us. So now I'll turn to ARC, because this is our compact, high field compact pilot plant. And And the rest of the talk will be about arc. So it's actually the same plasma science and magnetic field as spark, but the size is increased. And now you can see the person standing beside it here. The size is increased to be able to shield the magnets with a meter blanket, capture the fusion energy, and this produces at probably minimum about 500 megawatts of fusion power and over 200 megawatts electric power. But now the plasma duration is greater than an hour, not 10 seconds. So this will require active cooling and heat management of all the objects which are inside of this. So here's the cartoon again, here's the plasma, here's the other thing, and I'll show you about what we're thinking on this. So the key innovation in ARC is that it actually features demountable Rebco magnets, this which will allow modular replacement of internal components and the use of a liquid immersion blanket. So what do I mean by that? So I've got this toroid. So now the idea in ARC is that you can actually lift off the top part of the magnet, and the closed toroidal geometry, which is necessary for the fusion confinement, opens up to cylindrical geometry so that you can access those things which are inside, which are obviously the things taking out the heat. So what does this lead to? Is that this thing that you see in the surrounding the plasma is actually basically the single material or solid material object engineered component, which is interacting with the fusion heat. It's a close-fitting, thin toroidal vacuum vessel, which is designed to be replaced as a single unit. So all the fabrication can be done offsite, and it can last about a year from neutron damage and then be replaced. So this is itself as, although most people are familiar with fusion design, this is a kind of a radical approach to this, because in some sense what we've done is that we've minimized the solid materials that interact with the fusion environment by intentionally moving those solid materials up front, close to where they get damaged, but designing it to be replaced, not trying to make unobtainium. And then finally, the other key innovation was then the volume between the vacuum vessel and the magnetic coils is a bulk lithium-containing liquid blanket. It's essentially a big pool of this, that's why we call it the liquid immersion blanket, because the vacuum vessel, which is the only thing in the vacuum is needed for is the plasma, is on the inside and up close to it. So by definition, this can be replaced on the fly because you just pump it around. You get no damage limit from the neutrons because the neutrons can knock all they want into a liquid, but it doesn't care about its atomic ordering, and it serves as the global heat sink and working fluid for the fusion core. But what about the details of the cooling technology of this? Well, now let's get to some more numbers about ARC. So in fact, now I'm going to start showing more about from the design class, which is, you can see down here, 2263. Any MIT students interested in taking this, probably teaching it in spring of 22. This shows making, like, what's the power balance in this? So in the end, this particular version of ARC made a gigawatt of fusion power. And what you're seeing is a cartoon from a volumetric point of view. On the top is that it's making about 25 megawatts per cubic meter fusion power in the core plasma. And what this results in out in the blanket is like an average loading of around 5 megawatts per cubic meter in the salt. But as I told you before, other parts of it have to do with surface heating. That's on the bottom. And there we get a global level of around 0.5 megawatt per square meter. And a concentrated part in this diverter where we actually intentionally siphon off the plasma, it's more like a surface heat flux of around 3 megawatts per square meter. And this featured a whole set of designs that basically, that I can't go into all the details because it includes plasma physics as well too, about understanding particularly the plasma heating part of this has to do with the vagaries of plasma heat transport and so forth. But the cartoon is rather simple. It's like, oh, well, now I've got this material on the outside, and what I'm going to do is push this working fluid, I'll get back to the details, basically gets pushed down in here off past the heat exchanger, gets pushed into this thin vacuum vessel. You get forced convective flow through this. Very nice and very simplification, actually just empties out into this big volume of the liquid, and then you recover back this liquid out into the hot part of the heat exchanger. This is, of course, driving your turbines and so forth. And here we did some simple estimates of things like what were the total flow rates, like a few cubic meters per second basically is enough to establish thermal equilibrium, and the entirety of it has a reasonable flow speed, and you can see that it's a few atmospheres of pressure drop on this. But the actual details, of course, particularly when it gets into the high heat flux components, is much more difficult. And in particular those regions that I talked about where the concentrated power is, we have to deal with power fluxes which are well in excess of a megawatt per square meter of surface heat fluxes. So again, I can't really get into too much of the details, but to show you that this is the beginnings of thinking of innovations of what we had. So in our case, our working fluid is a molten salt. And what we were doing is we were trying to figure out if we could use like a pretty established technique like swirl tube technology to in fact enhance the heat transfer with reasonable amount of pumping power, reasonable amounts of heat transfer and pressure drops in this environment. And here you can see some examples of this. And the swirl tube technology has actually gotten repetitive, allowed surface heat fluxes up to 15 megawatts per square meter with water. Our indication was like the salt was kind of similar to that, but it was a pretty simple one. We also started considering things that for the construction of this vacuum vessel that we'd use like 3D printing, because it would allow us to put it like essentially build in internal swirl tubes, but have it instead of like, good structural meshes that would induce turbulent heat transfer and so forth. So our present leading candidate for this working fluid is FLI, which you're probably not familiar with. So this is a fluorine lithium beryllium salt, and it's a lithium containing molten salt. The reason that we use this is that it's molten from 700 to 1700 Kelvin. It's all single phase flow, like spectacular. Of course, the high temperature really helps with thinking about the overall economic mission for fusion as well too, for higher higher Carnot efficiency. Has low electrical conductivity, which vastly improves electromagnetic plasma control because there's much less stuff to go through electromagnetically. It has lithium, which provides the tritium breeding, and it radioactively decays to safe handling within a day or two. So it really is very attractive, and it's a highly efficient at slowing down the neutrons. Now, one of the interesting things over here on the right, though, is that as shown in a recent PhD thesis, in fact, she just defended last week. Congratulations, Caroline. I think she's watching. Caroline Sorensen, who is a MECI student at MIT. We've identified some unique challenges because although it has low electrical conductivity, it's not zero. And so what we're finding out is that it's sitting in a regime of Prandtl number versus Hartmann number that is actually totally almost unexplored, basically, in terms of heat transfer. So what's going to happen with respect to turbulent heat transfer when you've got a combination of a high Prandtl number, low electrical conductivity, and high magnetic field? Because this is an order of 10 Tesla magnetic fields. So what we're finding out is that over here on the right is that the magnetic field is inducing MHD effects, which are starting to suppress the turbulent heat transfer. And this is highly geometry dependent because the magnetic field topology of the tokamak is set by the plasma physics, not by the heat transfer. So you basically have to figure out clever things about how you're channeling flow parallel to B versus across B. There's also magnetic field gradients. All these things come into play with thinking about this. And really, in a way, we're just starting. This is a great PhD work, and we're already starting to see like we need to tackle this problem a much higher level of fidelity. Okay, so the last talks really. So I think hopefully that set up why the challenge is unique in fusion. Kind of our approach, high field, is going to make these devices, and as I showed you, it kind of like improves the economic prospects for fusion by an order of magnitude, but it also kind of almost by default increases the fusion power density also by the same factor. So we're really in this place where this says that it has basic viability, particularly with our approach with the liquid immersion blanket. But I would point out we need more and more innovations. So I'm going to use, there's a lot of work going on this, and maybe I'll add some of those in the questions. I'll use this as a case study on an example of innovations in fusion power removal. So this is the last 2263 class that I taught. It was last fall. So this is ARCH, which was essentially an ARC class device, which was being oriented rather to make hydrogen fuel. So the cartoon was as following: take something that has got the basic concept and an approximate size of what I showed you before for ARC, but instead of making electricity, we'd use fusion heat to make hydrogen and then ammonia, with the idea that we could actually have these as shipboard-based refineries that would make hydrogen and then ammonia that can be used rather routinely in long-range maritime shipping. So here's the cartoon of it down at the right. So essentially using fusion energy as a as a fundamental energy source to create a green fuel rather than to make electricity. And the very exciting in this one, and it's germane to this, is it's like that the target of this became not a technical target about some amount of power or power density or something else. I actually set an economic target for the class, which was, we decided, we had some external experts tell us that if we could sell this ammonia at about $280 per ton, we would basically decarbonize worldwide maritime shipping. So could we actually get there? So it ended up taking some real thinking, and it almost all came down to heat transfer. This is why I think it's germane to the colloquium. So we took an ARC class device, and in the end, this made about 1.5 gigawatts thermal. That was feasible within the design. And then we set up think about how we set up heat exchange into a secondary salt, helium Brayton cycle. We actually used some of the heat and generated some electricity in terms of the hydrogen production using the Haber-Bosch process for taking the molecular hydrogen, separating out the nitrogen, and then we came up with a target for the power plant of making about 2,600 tons per day of ammonia, and we got very close to our economic target of around $300 per ton, with the following efficiency, which you see up on the top here. But what did this take? Well, what this actually took was again, this isn't too much surprise. In an energy source that has no fuel costs, it's like your economics are almost solely driven by power density. And that's what we found, was that as you try to get low levelized cost of ammonia, this really was down into two things. One was for high heat exhaust, and high fuel density, which basically increased the fusion power density. So where we ended up was, there were some other things that happened in terms of the fusion design that we basically decided we had to eliminate any concentration of internal heating on the surfaces at all from the plasma removal. So we got rid of it. And the way that we got rid of it was that it turned out that it was an aspect of being able to access higher magnetic fields allowed us to actually very non-intuitively degrade the plasma confinement intentionally, such that what would happen is that we were intentionally, all that alpha heating that I showed before is intentionally being converted into photons and being uniformly distributed and isotropically to the first wall of the device. This just shows that the plasma physics works. I'm not going to go through details of it, but in the end, it showed that you could basically have this plasma being self-sustaining at 1.5 gigawatts of fusion power and basically need almost zero input power. So it has almost infinite energy gain on it. And that's actually this line that's going up along here. You'll notice, by the way, that there are actually points along this contour here that are actually at higher fusion power, up at 3,000 megawatts, but we couldn't use it, even though it's physically accessible, because we had no heat exhaust solution for it at that point. And that's actually in the end what it ended up being, is that it's the same cartoon that I showed you before, but the key one to show here is that the surface heat flux that we ended up with, now isotropically distributed, like the best theoretically you can do, was still at 1 megawatt per square meter of surface heat loading, along with the volumetric heating, which is coming from the neutrons. So we came up with two kinds of different innovations within this, is that we redesigned like the first wall. We redesigned the vacuum vessel, and we particularly used something called the LSVV, the liquid sandwich vacuum vessel. I'll show you that. And then we were using the liquid version blanket, which basically was still used pretty much intact from the previous design that I showed you. And we indicated that, in fact, we could reach the thermal heat removal of this, even though the fact that now we were actually pushing the global average up to like 5 megawatts per square meter, which is really pushing the frontiers of where this is. Yet we could even use more, in fact, if we came up with it. So what was this idea, this liquid sandwich vacuum vessel? And I'm not showing this that we proved it, that it works, but it's an indication of the innovations, I think, which are needed in heat transfer. So if we think about this cartoon of the vacuum vessel, it basically needs to have a structural material solely to provide vacuum integrity. So what we did was try to eliminate even more solids out of the material. with the idea that we'd have thin structure silicon carbide, solid structures, and then we'd have interleaved liquid layers. And what we have for interleaved liquid layers is a channel in here of liquid lead, not the salt, but liquid lead. And then on the outside, we'd have forced convective flow of the salt, which is the flibe. And then over on the far right is the global heat sink, the large blanket. This gives you an indication of the challenges of this, is that down below you see the temperature profile in Kelvin, because these are the heat fluxes which are in place. Silicon carbide doesn't have great thermal conductivity, so you can see that even though this is only a few millimeters thick, there's like a 200 Kelvin drop across this thing. But then across the liquid, it's that, then across the next solid. So every solid surface basically keeps adding to the delta T from the plasma surfaces all the way over to the liquid immersion blanket. So what was the idea of this is that basically was to get rid of more solid materials with the idea that we would try to have induced convective flow, particularly of the lead, that would actually enhance the heat transfer. The other challenge that the lead, and really primarily was there for, is that another problem or a challenge in fusion designs is that there's large electromagnetic loading, which is possible because of the large currents and forces, stored energy, which is in the plasma. And because the lead has 100 times higher electrical conductivity, basically all the structural forces get concentrated in the lead, which is good because it can't break. So in the end, we came up with a solution to this. It's really tough. You can see the kinds of levels of heating that we're talking about in terms of megawatts per cubic meter, from the plasma through the LSEV into the blanket. Here's that characteristic E folding length that I talked about before of around 20 centimeters. And you can see the upfront concentrations of all this power are now pushing into 40 and 50 megawatts per cubic meter. So in the end, we are forced to actually allow the temperature of the flibe to actually increase substantially, which is okay in general, but it actually was bringing in other challenges like around like corrosion control in the salt, but I'm not going to get into that. And in the end, we actually figured out we could actually make this work with flibe essentially being pumped around globally at about 1 cubic meter per second by submerged pumps. And just a little bit, and just don't finish, John. So the just as a cartoon to show you like what were we thinking of with this lead? As I said, it served a primary purpose of tolerating these large electromagnetic forces because you're basically shear stressing a liquid rather than a solid material. But how do you actually force convective pump lead? So one of the ideas that we came up with was to actually use MHD to our benefit in this sense. And so the idea was that what we were going to do was those very big magnets that we've built is put on a very, very slow oscillation of this by a trim coil that essentially push in and out the flux a little bit. So the plasma, it's never going to really care about this modest change in the magnetic field. But to any conducting liquid on the inside, it will have inductive currents, which will actually be forced into this. And if you build it the right way, this is essentially inducing a radial, in other words, in the direction of the heat transfer that you want, a J cross B force. It's actually a Lorentz force, which is trying to push the lead around in such a way as this. So in the end, we came up with a cartoon. We're not really exactly sure of all the details of this, but we figured out that actually this looks like it's got legs, that namely you could use essentially an electromagnetic pump action to actually force convective flow patterns to start forming in the lead and enhance the heat transfer that was going on there, but yet at a very low price in terms of power that you were paying, and no external pump needed to be hooked up to the liquid lead. This just is an indication of the difficulty of the structural, and I haven't really talking about the structural materials, but this gives you an example of what it looks like, is that it's really simple. You have competing processes. You want everything to be really, really thin for heat conduction, any solid surface, but thin is bad from a structural integrity point of view. So you've got to come up with lots of gains. And in what we've done in ours is we've considered silicon carbide, which has really great compressive strength limits. But then we basically are starting to, and particularly thinking about like using additive manufacturing to build internal bridges, if you want to think of it this way, in terms of the vacuum vessel structure, so that it's got viability in terms of stress and displacement, and actually can handle both the electromagnetic and the thermal stress loads, which are on it. Again, the thermal gradients are orders of hundreds of Kelvin per millimeter in these. So there's very large thermal stresses achieved in this. And this shows you some pictures about just the thermal stresses which are coming around from this. They are significant. We got it to a place where it seemed approximately viable, but we haven't actually answered this. And here I have to give a shout out to a major source of the funding of all this, which is Eni, which is the Italian energy company. By the way, if you want an indication that fusion is becoming more real, one of the largest energy companies in the world is sponsoring this research at MIT about looking at this, because one of the realizations is that we understand heat loss is going to be, heat transfer is going to be one of the limitations for practical fusion systems. So in the end, we actually took all of this and built an economic model around this, which was, we took all the aspects of the fusion power, utilization factors, the balance of plant, the hydrogen production, the ammonia production. And in the end, we took capital costs, annual operating costs, and all this came into a levelized cost of ammonia, basically, for the fuel. And as I said, this pointed the way to like both the promise of what we're doing, but also the challenge of what we're doing. The molten salt's operating at 1200 Kelvin, secondary salt at 1100 Kelvin. You're pushing efficiencies all to the maximus. And like, we don't have all of the material solutions, even about just the containment vessels of this. I mean, these are within the physics limits of the fly, but the practical limits of this are challenging. This is not surprising, by the way. This is also similar to the challenges being faced in like thermal concentrated solar when they're heating up salts, for example. And in the end, we got all these efficiencies. But I wanted to finish with this last one, which is that what I really got a kick out of, this is the first time we built an economic model in the class, is that we basically checked out the sensitivities to the different things of like, how was it affecting or not affecting the price of the ammonia, basically hitting the economic targets. And this shows the relative sensitivity compared to the point design, which ended up at $300 per ton. And what you can see in this is that all the sensitivity, like if you basically, so what does this say? That if we can increase in the red one, the fusion power by 20%, like we drive the price down such that it actually beats every other source of fuel, even fossil fuels actually at that point. But if you're 20% less power, then it's starting to climb it up. I was like, oh, well, we basically figured out the global sensitivity to power exhaust. Because if you can't get the fusion plasma could clearly make this amount of fusion power. If we could squeeze out another 10 or 20%, oh, the economic prospects are so much better. Well, of course, this is totally logical. And we know this from our fission cousins as well, too, as I described before. There's other things which came into this, which is like that basically the peak power cycle temperature. Oh, yeah, it's Carnot. That comes into place. And the cycling limit on the fatigue of the materials, which are being stressed and unstressed from the thermal loading. So what this said is like, it's like, if you can, I'd summarize this, if you can make the magnets work, your challenge isn't any, I shouldn't be so sanguine as that, but it looks like the biggest challenge is heat exhaust, not the fusion plasma physics anymore. Because you basically cannot exploit to its fullest that ability without pushing more and more on heat exhaust. And that's an interesting challenge. So I'll summarize there. Really, the summary is this disruptive magnet technology. And I'd point out the emergence of a very thriving private sector fusion industry, which MIT helped to launch, but it's also going in other places as well, too. And the fact that large global energy companies are coming into fusion, it's really accelerating the pace to net energy fusion systems. It's the most exciting time in fusion, I think, ever. But this also makes exploring innovative heat exhaust solutions more pressing. This isn't a problem that's going to appear 30 years from now. Like, we need to be working on these problems now, which is what we're doing. And the fusion environment is unique in terms of heat exhaust. The combination is really energetic and damaging particles, plus high magnetic field, plus vacuum, plus toroidal geometry. All these things are very unique to this. And then, as I pointed out, the geometric challenge, all energy removed through a single remote surface. So all I would conclude is the pathway to practical fusion energy systems and economical energy fusion systems clearly requires further innovations in thermal heat exhaust.
Thank you, Dennis. That was fascinating. And it's a really impressive combination of engineering challenges that you've you've come to here. So for those in the audience, please put your questions into the Q&A. I'll give you the first one, Dennis.
Sure.
This is from Charles Witoski. Given that superconductor innovations have allowed for such dramatic size reductions, is it likely that future superconductor advances will allow for even more compact designs? Or is that no longer the limiting factor for further size reduction?
Yeah, that's a good question. So actually, it has to do for deuterium tritium fusion. This will be probably the size limit, and it actually comes because it's nothing to do with the confinement of the plasma. It's actually the fact that you need a certain amount of space to stop the 14 MeV neutrons. So in a magnetic configuration, that kind of like sets a limit, and we think that we've kind of basically in the ARC design we have hit that limit. So that's one consideration. The other one, which is actually in some sense the more frustrating one about fusion, is that you also hit a power limit, and a power limit the other way, like on the bottom end. Because fusion self-sustains itself through heating, it turns out if you take it at a high enough level, you find that there's kind of a minimum amount of fusion power at which you can also get net energy gain. And that tends to be around, this 10 to 50 megawatts, which is where spark sits as well to that. So it would be nice if we could think about going to even smaller size, and particularly smaller total power output, because that could also increase the economic prospects, I think, for fusion. But right now, the physics doesn't really lend itself to that, which has also been one of the challenges of making fusion work. That spark, as I said, is 40 times smaller, than ITER to make net energy for the first time. Compare this to our fission cousins. Fermi got the first sustained chain reaction at 1 watt. We're doing ours at 100 megawatts, and that actually comes from the physics of fusion. There's a reason that I think once we're over that threshold, we can take it on. So we think the superconductors are good enough, but we're always looking for more innovations in that result.
We have another question. This is from I'm sorry, I'm going to mess up your name, Melanie Tetro, friend.
Melanie, sure.
Okay, good. You know each other. So Melanie's question is, thanks for the exciting talk, Dennis. How sensitive is the entire spark system to impurities in the flibe salts? Do you expect you will need to continuously filter the salts or reload with fresh salts?
Yeah, so it's a good question. So the overall performance of the salt is not greatly impacted by impurities in the salt, just because it's very difficult to worry about the. In fact, the salt is a lifetime component essentially in ARC, because your relative amount of depletion of the materials in it is so small, relatively small, you can kind of keep it in there. The challenge for impurities is twofold. So actually the answer is yes, we have to keep the salt pure, but it's not for the reasons as you think that it would mess up the fusion part of this. It actually messes up important but more prosaic things. Number one is that if it's starting to impact the electrical conductivity of the salt, then that would actually play a role, because as you increase the electrical conductivity, it takes more pumping power and all other conditions fixed. So we worry about that. And two is that the impurities in the salt are the primary feature of what would set the radiological profile of the salt following the completion of it. If you can keep the salt pure, and it's because there's only low, the nuclear physics of this is only low atomic number things, fluorine, lithium, beryllium. So they make temporarily activated components, but they have such short half-lives that basically it's non-radioactive after a day or two. That's like an immense advantage, to realize, the safety feature of fusion. But if it's got even small amounts of impurities, like flakes of metals and things in it, that will dominate its radiological profile rather than the salt itself. So those are the two reasons we would keep it. Actually, there's a third reason, which has to do with the special needs for recovering the fuel. So the fuel is very dilute, the tritium fuel, which is very dilute in the molten salt. So the other reason to control this, in some sense, it's I call it the chemistry or the purity, if you want to call that the purity, the redox potential of the salt is necessary for controlling the form of the tritium that is there and your effectiveness of being able to recover it. So that becomes like a physical chemistry challenge, which we're starting a project on as well too, on that one.
So one of the things that I noticed, Dennis, was that materials selection is a crucial part of the heat removal in this system. You have silicon carbide as a candidate material at high compressive stress, relatively low thermal expansion, reasonable thermal conductivity. What sort of material innovations would you be seeking around the solid side? People are very interested in what they can do to raise conductivity of solids and other features.
Yeah, it's a very constraining set of requirements. So usually, the leading ones are, in fact, silicon carbide is not the leading one. We're kind of taking a chance on seeing if it can work. The leading candidate is usually refractory metals, so particularly tungsten, because it maintains fairly high thermal conductivity even in a neutron environment, but it's got other challenges around the fact it's so brittle. Yeah, you have to, the ductile to brittle transition temperature changes as you irradiate it. Almost to Melanie's question, very, very teeny amounts of this that kind of get removed into the plasma are so poisoning that they would basically stop the fusion reaction. So it has its own challenges, not to mention avoiding the melting problems that would come with tungsten, because the plasma in a few milliseconds can, if it decides to and gets uncontrolled, can basically melt interior surfaces just because of those crazy thermal heat conductivity numbers that I gave you. So, but that tends to be but tungsten's got some other great properties, namely it's high thermal conductivity. It's very resistant to any removal by the hydrogen species under normal conditions because it's such a heavy element, and it has a very high surface binding. It basically has a high melt temperature. So that's really good.
Sorry, go ahead, please.
Yeah. So that's that one. So those would be the two leading ones for what actually looks at the plasma. For what's the structure of actually what the vacuum vessel is made out of is there's a whole set of choices there. It's immense, actually. There's reduced activation ferritic materials, ferritic steels. And all of them bring their own challenges. Some of them have crappy temperature windows, are not as good temperature windows. Some of them are more prone to like swelling in the neutron environment. So they push out, they basically expand because of that. Some of them are worse from an activation point of view, like anything that contains nickel is like a really bad actor in terms of activation. Vanadium is another choice, which is sitting there, which turns out it has great nuclear properties. So it's this weird space that we have to go into. And by the way, part of the other challenge of all those structural materials is not going to say we fly blind, but we've never really made, it's the weird thing about a fusion device is that like to actually test in an integrated way, all these actually need in some way a fusion power plant, because there is no intense source of 14 MeV neutrons anywhere. And all the other things that come with the thermal environment. So it was actually why I designed, I should, comment to what is ARC. Our ARC, when people see ARC, they go, oh, that's your design. Are you going to use silicon? Can you really use silicon carbide and all that? It's like, that's actually not the point of ARC. One of the points of ARC is that the general concept of the fact that you could try different structural materials for the vacuum vessel. And if it fails, you can replace it and learn by it, was at the heart of, in fact, the strategy of ARC. And I think why many of the private sector investors in Confinement fusion systems came along. We didn't pretend to have the answers, but we've got a strategy to find practical answers. So the answer to your question is, if you've got a great idea that can satisfy all these criteria, we'd love to hear it about the structural materials. And we do have people like Professor Mike Short, for instance, in nuclear science and engineering, who's a real expert in this. We're starting to go down that pathway of trying to get higher fidelity data about meeting all these requirements simultaneously.
Yeah. Well, my experience in high heat flux engineering has been that often the barrier is getting the right experimental vehicle to get the high flux.
Exactly.
That's the wall you hit easily. So.
And it's a, well, yeah. So we're working on different tools. It's really become a lot more of my of the focus for the future of the Plasma Science and Fusion Center is really moving, you know, with support from our sponsors like NE and CFS is really moving into these engineering problems that are around not just trying to come up with unobtainium, which is a bad strategy. It's really coming up with a toolkit that you can actually assess materials and heat transfer in a more realistic way. And again, the answer eventually will come in actually operating a spark and an arc. But that's not an excuse. We got to be thinking about clever ways to basically get to more typical, prototypical environments. And I've got a whole set of slides on that already. And we're working on some of those ideas at the PSFC right now. Yeah.
Yeah. I encourage audience members to put questions into the chat. Dennis, two materials that are sometimes mentioned for high flux applications are molybdenum and tantalum.
Yeah.
Are they compatible with the kind of environment that you have?
Tantalum. I'm not that familiar with tantalum. It's probably I can talk to molybdenum. So molybdenum was used, in fact, a lot in the fusion experiment Alcator CMOD at MIT. That was the experiment that we ran on campus that achieved that actually showed us that the high field approach works. The interior components in that were inertially cooled molybdenum. So much like tungsten, it's really good because it's got great refractory metal, high thermal conductivity, easier to work with than tungsten, less brittle conditions. The problem is its activation profile in a neutron environment, very poor. That's so, yeah. So I'm not gonna, it eliminates molybdenum, but close.
Yeah, yeah.
And it's probably, I've never really heard of people talk about tantalum, so I suspect it's probably off the, like when you look at the periodic table, you almost automatically, you cross off about 90% of the periodic table, unfortunately.
Right. Yeah, tantalum found some applications to rocket nozzles, I think, in the NASA.
Yeah. It's the neutrons are weird, and that's not really like it's really nuclear engineering, right? At that point, it's like the particular isotopes which are made that they've got a high probability of particular kinds of reaction. It makes them very, very difficult to work with. Of course, one of our long-term goals in this, and this is why silicon carbide is attractive, is that it's got a very low radiological profile because it doesn't contain any high Z elements in it.
Right.
Yeah.
Grand. Well, Dennis, thank you. I see no new questions coming in. Folks out there in the audience land, last chance. Meanwhile, I am going to now just wrap us up. And I'm going to do this with just 2 slides here. Oh, wait, something popped in here. Hang on. Got one more question. Oh, there's an anonymous attendee, and it's a joke that I don't get. I thought Tony Stark told us in a cave.
I just read that. Okay, let's be clear about this. So, as I said, this is a little bit of whimsy in it. So this was ARC was conceptualized in my fusion design class 2263. And the students put in an enormous amount of work to it, and because in fusion we always have to come up with acronyms to describe things. So ARC stands for affordable, robust, compact. It is an acronym. It does not reflect Tony Stark's ARC fusion power plant that was in his movie in Iron Man. Warner Brothers or whoever owns the copyrights to that. So.
Peter Kato has got a question. The neighboring solid surfaces have to support the weight of the liquid lead. Is this an issue for hydrogen production? The
supporting the weight of the lead is, yes. So In fact, it's that, and it's the weight of the flibe surrounding the entire tank. So I didn't get a chance to show it, but one of the assessments in this is it just like in a static sense, is it structurally okay because of this. It's a very unusual vacuum vessel because it floats in a rather high mass density fluid. In fact, it's interesting in that picture, the cartoon that I showed you, the vacuum vessel's buoyant in the fluid, in the liquid salt.
Wow.
So it's kind of like building a strange submarine vessel with a sun. So yes, so the weight does matter in that, both for the lead, but it's actually primarily driven by the salt because there's so much more of it. It's about 200 tons of salt, I think, in there. It's basically a big salt swimming pool with an immersed with an immersed vessel inside of it.
Oh my goodness. Okay, folks, thank you all. Couple of closing remarks here. In terms of what's next, Inotherm will be taking a break over the summer. We will kick off in September with additional information on Inotherm Colloquia. So we're going to wish you a happy summer, time to catch up and recover from this remarkable year that we've had. You can find the past recordings linked off of the Inotherm webpage into YouTube. This webinar will also be posted relatively soon. If you have any suggestions for future events, speakers, topics, or formats, please put them in the chat or the Q&A here, or just email us. You're also encouraged to sign up for our email distribution list, which is available on the Inotherm webpage. So thank you all. Particularly thank you, Dennis. Really enjoyed the talk today.